Forces includes two pieces. Number one, moving electrical charges produce a magnetic field throughout space. Number two, other moving electrical charges feel magnetic fields that they're in. So we're going to deal with the first part right now. Moving electrical charges produce a magnetic field. So what do I mean by moving electrical charges? Well, here's a vertical wire. It's hooked up to, at the top, and the bottom, it's hooked up to another circuit somewhere, batteries or something that end up producing a current, an electrical current, that goes straight up the page through this wire. And our model is that that current produces a magnetic field that circles around the wire in the way that's shown here. So the magnetic field is circling around in this way. These are magnetic field vectors. As you can see, when you get circles around this wire that are farther and farther away, the magnetic field vector is getting shorter. In other words, the magnetic field is getting weaker and weaker as you move farther away from the wire. If you are in front of the wire, the magnetic field is to the right. If you are over here to the right of the wire, the magnetic field will be directly into the screen, and it comes around. And if you are behind the wire, the magnetic field is to the left. It continues around. If you are to the left of the wire, way over here, then the magnetic field is out of the screen, and then it comes back again. So this is a bunch of magnetic field vectors. So everywhere along this thing, there's magnetic field vectors circling around the wire. This was a magnetic field vector picture of the magnetic field. I can do a field line picture where I don't draw the vectors, but I kind of connect them up, and this field line shows the direction of the magnetic field vector at any particular point. The density of the field lines, how close they are together, tells me about the strength of the magnetic field. So they're closer together near the wire, and as you get farther from the wire, they're farther apart. Now we have an equation that tells us how to calculate the magnetic field given this current. It's called the Biot-Savart equation. It has a few pieces. The current is going up the wire. Current is I. dl is a small piece of this wire, and it has a direction, and the direction is the direction of the current. So the direction of dl is up the wire. R here is the distance from the wire. So I want to know the magnetic field way over here. R is the distance from L. If I want to know the magnetic field down here, due to this piece of the wire, R is that distance down to there. Notice that's kind of a long distance, and so that's going to be a smaller magnetic field than the magnetic field due to this part of the wire, which is where R is this and this smaller number. You'll see that there's a cross product between dl and r hat. R hat is the unit vector in the r direction. Because there's a cross product, you probably know that there's a right-hand rule that tells us the directions of the vector. The particular right-hand rule for the direction that the magnetic field circles around a current is point your thumb in the direction of the current, your fingers curl around in the direction that the magnetic field points if you're using your right hand. In other words, with your thumb upward, your fingers curl in such a way that if I look down on them, they are curling in a counterclockwise direction. They are pointing around this thing counterclockwise, just like the magnetic field is circling around this thing counterclockwise if I look at it from above. Let's look at this magnetic field from the top. You can see that if I look at it from the top, the current will be coming at me, and the magnetic field will circulate counterclockwise around the current. So here's a picture of that. The current is pointing at me, so that's what this circle with a dot means. Magnetic field vectors circle around that current, and the vectors get shorter and shorter as you get farther away. What if the current was in the opposite direction? Here's an arrow that points away from me, showing that the view from the top, if the current was going down, or a view from the bottom if the current's going up. But in any case, the current here is into the screen, and your right-hand rule shows you that the magnetic field circulates around clockwise. One thing about these magnetic fields, just like electric fields, they're everywhere in space, right here, up here. Even though I haven't drawn a vector, there is one. It points in that direction. It's pretty small. I haven't drawn them because they're so small. Way up here, there's one that points like that, but is really short. Down here, there's one that points to the left, but is really short. So everywhere, even if I haven't drawn one, everywhere in space, you can draw a magnetic field vector due to this particular wire. So now we're going to put two of them on top of each other and think about the two together. On the left-hand side, I have a wire right here. On the left-hand side, there's a dot in the center, so the current is going toward me. On the right-hand side, I have another wire, same current, but it's away from me. So same magnitude current, but it points away from me into the screen on the right, out of the screen on the left. I changed the colors on the arrow so we can separate the two. But your right-hand rule tells you what's going on. In the center here, the right-hand wire that has the current into the screen is producing a magnetic field that's upward. The left-hand wire that has a current coming out of the screen is producing a field that's upward. Those two magnetic fields add together to give you a large magnetic field pointing straight up in the center. What about farther up here? The wire on the right, when you're way up here, it's producing a magnetic field that goes up and to the right. The wire on the left is producing a magnetic field, when you're way up here, is producing a magnetic field that points up and to the left. So the end result of up and to the right and up and to the left is a vector straight up. So when you're up here, the magnetic field points straight up when you're in the center. When you're in the center here, it points straight up. How about down here? Well, you can see that the magnetic field due to the wire on the right points up and to the left. The magnetic field due to the wire on the left points up and to the right. So the left and right parts cancel and you get a magnetic field pointing up. The end result, everywhere along this midline, the magnetic field points up. So this is going to be a magnetic field line that's just vertical here, straight vertical. What about closer to this right-hand wire? Well, closer to this right-hand wire, the magnetic field is really big. I haven't drawn it. It's a gigantic vector here. It's twice as big as that one. Twice as big a vector up. The magnetic field due to this one is up but smaller. So there's a really big magnetic field right here. And not surprisingly, when you get close to this wire right here, the magnetic field is just going to circle around it just like it did by itself when that other one was missing. And when you get close to this wire, the magnetic field is going to circulate around it counterclockwise just like it did when that one wasn't there. So when you're close to the wires, the magnetic fields look like they did by themselves. Everywhere in between, the magnetic field is gigantic. So these magnetic field lines are going to be close together in between because the magnetic fields are so big. The magnetic field line is going to be vertical in the center, and out to the right of both wires, the magnetic field due to the right-hand side is bigger than, but partially canceled by the magnetic field due to the left-hand wire when you're out on the right. So smaller magnetic fields out here because they're partial cancellation, and smaller magnetic fields out of here because the magnetic field downward due to the left-hand wire is partially canceled by a small magnetic field upward due to the right-hand wire. So here's the magnetic field line picture that shows you basically that magnetic field line is vertical because the magnetic field in the center always points straight up. In the center, the magnetic fields are large, so these lines are dense. And on the right, the magnetic fields are small because they're partially canceling, so these lines are not so dense on the right. These are the magnetic field lines of the total magnetic field of two wires whose currents are in opposite directions. What if the two wires have currents in the same direction? The one on the right has a current pointing out of the screen. on the left has a current pointing out of the screen, so they each circle around. And you can see what happens here in the center is that there's a downward magnetic field due to the one on the right, an equal and opposite upward magnetic field due to the one on the left, at least if the currents are the same, and they are, then this is going to be 0 in the center. There's kind of partial cancellation in the center here. 0 magnetic field means that the magnetic field lines in the center are going to be farther apart. What if I am in the center but higher up here? Well, the wire on the left produces this magnetic field that's up and to the left. The wire on the right produces this magnetic field that's down and to the left. If both of them are to the left, the up and down parts cancel. You end up with a magnetic field to the left right here. Similarly, down below, you end up with a magnetic field to the right. So the magnetic field is to the right here. If I look at the magnetic field over here on the right, both of them add to each other, so you get a magnetic field up. If I look at the magnetic field on the left, they add to each other, so you have a magnetic field down. So here it's down. The magnetic field lines are going to be pointing down. When I get around to the bottom, they're going to be pointing to the right. When I get over here to the right-hand side, they're going to be pointing up. When I get up here to the top, they're going to be pointing to the left. The end result for the field lines, 0 in the center, so not much magnetic field in the center. Denser lines on the outside, and the magnetic field to the right here, up the page, left, down the page. And as you get farther and farther away, they get less dense.